This time around we're going to learn how to use calculus to find the work done by a variable force. So work in this case is a mathematical idea, and this will be yet another application of integration. So this will fall in line with our arc length and area of a surface and volume of a solid revolution. So first let's define what work is. So work done by a constant force, if an object is moved a distance d in the direction of an applied constant force F, then we define work, which we'll call W, as the product of the force and the distance that it's moved. So work will be a constant force times that distance. So force can be thought of as the push or pull that changes the state of rest or state of motion of a body. So for example, determine the work done in lifting a 50-pound object 4 feet. So work is a constant, in this case, constant force times the distance. So work would be, it's a 50-pound object, and we're going to lift it 4 feet. So the work would be 200 foot-pounds. So 200 foot-pounds. Well, what if the force varied? So what if it wasn't the same amount of force all the time during the situation? So let's consider an object that's being moved along a number line from x equals a to x equals b by a force that depends on x. And so just for convenience sake, we'll have the object moving along a number line so we can easily determine position and distance. And we'll have our force depend on some number x this time. So the force will vary depending on what x is. Okay, so let's go ahead and divide our interval a to b into a finite number of subintervals called n. So n subintervals, where our left endpoint a will be equal to x sub 0, which is less than some x1, which is less than some x2, and then x sub n will be our right endpoint b. So we have these subintervals, x0 to x1 or x1 to x2, so we've chopped it up into n subintervals. We're going to let the change in x sub I be the width of a particular subinterval. So x sub I minus x sub I minus 1. So this is the width of the ith subinterval. So let's say I was 2. Then you'd be going x2 minus x1. So that'd be the second subinterval, because x0 to x1 is the first subinterval, and then x1 to x2 is the second subinterval. So now for each I, so for each subinterval, we're going to choose an x value within that subinterval so it'll be somewhere in the subinterval. Then, at that x value, the force is whatever capital F is evaluated at that x value. And the work done on that interval is approximately, so we'll do the work for that subinterval, so it'll be the force times the distance moved along the number line for that subinterval. So this is all within one subinterval. So we've got the distance covered by that subinterval, we've got the force done, so force times distance give us work. Now that one x value is just approximating the force for that subinterval, so that's why this is an approximation. So let's say you wanted to go from A to B and see what the total work done is. Well, you can just find the work for each subinterval and add them up, and that'll be a good approximation. So from x equals A to x equals B, the total work is approximately so total work would be approximately the sum of all the work done on each subinterval. So we take our constant force times our distance. But as we've seen many times when we are applying definite integration to these real-world situations, that's if, so now that we have a finite number of subintervals and we sum all those up, we get an approximation. So if we want the exact work done, just let the number of subintervals approach infinity, which shrinks the widths of each subinterval closer and closer to 0. And then we get a Riemann sum, which we know a Riemann sum is behind the definition of a definite integral. So now we're just going to go the definite integral a to b of the force times a tiny change in x. So this delta xi, which is the width of each subinterval, as you let n go to infinity, it shrinks closer and closer and closer towards 0, so it becomes infinitesimal, which is what dx represents. And then instead of f at a particular x value, we'll let x vary, and then so our approximation becomes exact when we let n approach infinity. So now we're ready to define work with a variable force. So work for a variable force. So if an object is moved along a straight line by a continuously probably better, varying force f of x, so f of x has to be continuous, then the work done by the force from x equals a to x equals b is given by our newly created definite integral. So that's the force, that's a tiny change in x or a distance, and we're going a to b. So it's like we're adding up an infinite number of values of work along that interval A to B. So let's give this a try. So a force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. Find the work done in compressing an additional 3 inches. So we've got this spring that if you just kind of let sit there, it's 15 inches long. So then we've got this 750 pound force that's going to compress it 3 inches. Now we need to find the work done if we compress it yet another 3 inches. So Hooke's law, which you may or may not know. If you don't, it's no big deal. We'll give it to you here. Hooke's law says that the force in this case will be a constant times the distance compressed. Well, we know that 750 pounds compresses at 3 inches. So 750 compresses at 3 inches. So K for this particular situation is 250. So for this particular spring in this situation where we have a 750 pound force compressing at 3 inches, the K value is 250 for Hooke's law. So if we did a different spring with a different amount of force, that would change everything. But for this one, K is 250. So force for this situation is 250x. Because if x was 3 times 250 is 750. So the work done to do an additional 3 inches, well, remember, it's already compressed 3 inches. So now we're going to do another 3. So we're going from the 3 that's already been compressed, another 3 to 6 inches now. And then our force is 250x. And then our tiny, tiny infinitesimal change along the interval is dx. So that's a fairly straightforward definite integral. So we get 3,375 inches pounds. Instead of foot pounds, we have inches pounds. So the total work done is 3,375 inches pounds in that situation. So remember, it's already being compressed 3, and then we're pushing it another 3 on top of that. Let's take a look at another one. So in this particular setup, we have a spherical tank. It's got a radius of 8 feet, and it's half full of oil. The oil weighs 50 pounds every cubic foot. Find the work required to pump out the oil through a hole in the top of the tank. So you put a hole in the top, and you're going to pump out all this oil. So here's a picture of the situation. So if we put the base of this tank at the origin of the XY plane, we've got this sphere where the y-axis is running up through the center, and the x-axis would be acting as the diameter of any circle that comprises up this sphere. Okay, so to handle this, we would think of the oil as being divided into disks of thickness delta y and radius x. So by placing the sphere where we do on the x and y axis, then if you just think of one slice of oil, then its thickness is just some change in y, because that's the y-axis there, and then its radius will always be the x-coordinate, because you go from the center out to the edge of the circle along the x-axis, then its radius would just be some value of x. So it just makes everything convenient if we think of our spherical tank in that exact location on the xy plane. So our force, so we have 50 pounds per cubic foot of oil, so our force is going to be a weight in pounds, because it's 50 pounds per cubic foot. So we have 50 pounds per cubic foot. And if we were to multiply that by some volume in cubic feet, then the result would be some amount of pounds, which is what we need, because our force needs to just be in pounds. Well, so in this case, we're going to have 50 pounds per cubic foot, and the volume, well, let's see. Volume's going to be area of a circle would be pi radius squared times the thickness, cubic feet. So we've got this disk. So one disk of oil is going to have a certain amount of volume, and that volume is pi radius squared times how thick it is. So it's a disk, or a cylinder. So volume of a cylinder here. So we've got the area of the base, which is pi radius squared, but the radius is just x, times its height, which is delta y. So now if you multiply those together, we get 50 pi x squared delta y pounds. But we've got x's and y's involved here, so we need a relationship between x and y. So how are x and y related in this case? Well, we have a sphere whose center is 0, 8. So how tall? So the radius is 8 feet. So if the radius is 8 feet, that means the tank is 16 feet tall. So its center is going to be at 0, 8, based off where we placed it on the xy plane. So we're going to have x squared plus y minus 8 squared equals 8 squared. So this sphere in 2 dimensions is just a circle whose center is 0, 8, and radius is 8. So we use our equation of a circle to relate x and y. So basically we get that x squared is 16y minus y squared. So now 50 pi x squared delta y, which is our force, is actually just 50 pi. X squared is 16y minus y squared delta y pounds. So now we have only y's involved. And this is our force. So as each disk, remember we're thinking of this oil as comprised of a bunch of disks, as each disk is pumped out, it is moved a distance of 16 minus y feet. So let's go look at the picture and see if we can't figure out what we mean by that. So let's say you're grabbing the very top disk. So it's got to move 8 feet to get out the top. So that'd be 16 minus 8, which is where the center of that top disc would be. But if you're at the very bottom, then you got to be pumped out all 16. So when y is 0, you're being 16 minus 0, 16. It's got to come all the way from the bottom out the top. So now, the work done let's see, our force is 50 pi 16y minus y squared dy times the distance, which is 16 minus y. So here's our force right here. That's our force. And there's our distance. And we've just got to get this oil up and out of this 8 feet of empty tank. So it's going to go 0 to 8. So it's a polynomial. You can distribute. The integration is fairly straightforward. We get 50 pi 11264 over 3, which is about 589,782 foot-pounds of work. So the work done to pump this oil out is almost 590,000 foot-pounds. So something to consider. The oil, all of the oil weighs, it's half the cylinders filled with oil, right? So it'd be half 4/3 pi r cubed times 50. So that's volume of a sphere, but we only have half of it, and that's how much it weighs in pounds per cubic foot. So the oil itself weighs 53,616.5 pounds. So that's just how much the oil weighs inside this tank. So if we lifting the oil 8 feet would require, let's see how much work that would be. So that work would be 53,616.5. Moving a distance of 8, that would be 428,932 foot-pounds. So if we just moved it 8 feet, then we would only need 428,932 foot-pounds. However, we are moving the oil from 8 feet to 16 feet. So not from the bottom, only 8 feet up, but from 8 feet up all the way out to the top. So more work is done in that case. So if we were just going to grab this oil from the bottom of the tank and lift it up 8 feet, we would only need just under 429,000 foot-pounds. But since we're going from 8 feet up and out the top, which is 16 feet above the ground, but from the bottom of the tank, we need quite a bit more work. It's almost 590,000 foot-pounds. Let's take a look at one more. A 20-foot chain weighing 5 pounds every foot is lying coiled on the ground, how much work is required to raise one end straight up to a height of 20 feet. So again, our force, because it's 5 pounds per foot, is going to be a weight in pounds. So we have 5 pounds every foot. So if we multiply that by some length in feet, that'll leave us with just some number of pounds. So in this case, let's just think of the chain as divided up into small little sections, each with a length of delta y. So we get 5 delta y pounds. So delta y is just the length in feet of a section of chain. So basically take the entire chain and break it up into a finite number of little sections. Each one we'll call some change in y. So we're lifting it straight up, kind of like the y-axis. So y just makes sense here as our variable. So delta y is just the length in feet of a section of chain. And then our distance you're just going to, since it's coming off the ground straight up, it's just going to be y feet off the ground. Since the ground is like 0, like the x-axis, and we're lifting it straight up. So our work, well, we're going from the ground all the way up to 20 feet. Our force is 5 delta y. Our distance is y, so there's our force, that's our distance, and so we're basically just doing 0 to 20 of 5y dy. So our delta y, we're letting that shrink closer and closer to 0. So we'll use dy for that infinitesimal. So we do that definite integral, and it's going to require 1,000 foot-pounds of force to lift that particular chain 20 feet off the ground.